Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
You know, when you step outside on a really clear night, away from all the city lights, and you just look up, there's this overwhelming sense of profound peace.
Oh, absolutely. It feels completely still.
Right. The firmament just seems static. It feels permanent, you know? Like you are looking at the exact same constellations that your grandparents saw.
The very same stars that ancient navigators used to cross oceans.
Exactly. I mean, Aristotle and the early philosophers literally thought they were perfect, unchangeable crystal spheres. It gives off this really profound illusion of stillness.
It is the ultimate cosmic sleight of hand.
Yeah.
Yeah, because we are looking up and seeing what looks like a tranquil, frozen painting. But the reality is that we are staring into a relentless, violently chaotic engine.
And that stark contrast is exactly what we are unpacking today. Because when you strip away that illusion of peace, that sort of atmospheric trick that makes everything look like gentle twinkling pinpricks, the actual physical environment up there is terrifyingly turbulent.
It really is.
We are talking about giant, sprawling factories of freezing gas that are constantly just tearing themselves apart from the inside out. And they do all of this just to give birth to stars.
Right. And moving past that romanticized view of the night sky, actually looking at the underlying physics, it's a phenomenal shift in perspective.
It changes everything.
It really does. You have to stop seeing a quiet vault and start seeing a churning, violent, and honestly, a surprisingly fragile ecosystem.
So our goal for this conversation is to take you deep into the hidden, tumultuous life cycle of what astrophysicists call giant molecular clouds.
The universe's star factories.
Exactly. By the time we wrap up, we want to understand how entire galaxies function, not just as, static, dead collections of stars, but as living, breathing, self-regulating systems that actively manage their own survival.
But to pull that off, we have to completely overhaul our standard human perception of time, scale, and, well, even what we consider to be destruction.
Right. Think of it like looking at a photograph of a bustling, massive city like Tokyo.
Okay, I'm picturing it.
But the camera shutter was so incredibly fast that every single car, every person on the street, every pigeon mid-flap is just perfectly frozen.
Right.
If you had no concept of what a city was, you might look at that photo and think, wow, what a quiet, motionless landscape.
Which is essentially what humanity has been doing for millennia when we look at the Milky Way.
Exactly. We're looking at a frozen fraction of a second snapshot. So today, we're basically hitting play on that cosmic time lapse.
And hitting play is really the only way to reveal the underlying machinery. But before we can watch the gears turn, we have to talk about the sheer volume of data that makes this new understanding possible in the first place.
We have to zoom out, right?
Right. We have to zoom way out from our own local neighborhood to a multi-galaxy perspective.
And this is where the recent leaps in observational astrophysics just completely blow my mind. I mean, we are looking at an analysis of a staggeringly massive data set.
It is massive.
We are talking about more than 100,000 giant molecular clouds. And they aren't just local to our own spiral arm either. They are distributed across 66 different galaxies.
The scale of that leap just cannot be overstated. I mean, for a very long time, astrophysics, especially when it came to understanding star formation, it was severely handicapped by what you could call small sample limitations.
Because we were basically stuck trying to map our own house from the inside out.
Precisely.
We just had the Milky Way, maybe Andromeda, and the Magellanic Clouds to look at.
Yeah, and that is a huge problem. Imagine you were an ecologist trying to formulate the fundamental laws of how forests grow, but you were only permitted to study 5 specific trees in your local neighborhood park.
Okay, so a very limited view.
Very limited. And you might observe that, say, 3 of those trees have a very specific, strange fungus on the bark.
Right.
So you have to ask, is that fungus a fundamental biological property of all trees on Earth? Or is it just a weird local anomaly because the park's sprinkler system is broken?
Oh, that makes total sense.
When you only look at the Milky Way, you run into this exact statistical wall. You simply cannot distinguish between a local irregularity, like a cosmic quirk, and a universal physical law.
It is exactly like trying to figure out the absolute fundamental rules of human traffic by only observing one specific intersection in your hometown.
Right, just watching one street corner.
Yeah. You sit there with a clipboard, you watch the cars, and you notice everyone is driving in a circle. So you write down in your notebook, universal law of traffic. All vehicles must drive in a slow circle.
Because you assume roundabouts are a fundamental law of physics for cars.
Exactly. But that's only because you haven't looked at 66 other cities where they have four-way stops, overpasses, and traffic lights.
And for decades, that was the ultimate frustration. Many of the long-standing mysteries regarding how stars form haven't stuck around because we lack the theoretical physics to explain them.
The math was already there.
The math has been sound for a long time. The bottleneck was entirely observational. We just couldn't test those complex thermodynamic theories against a large enough, diverse enough data set to see what actually holds true in every environment.
So how do we finally get past that bottleneck? Because, you can't just point a backyard telescope at a galaxy 50 million light years away and start counting the gas clouds.
No, definitely not.
What is the actual mechanism that lets astronomers see 100,000 clouds across 66 different cities?
Well, it requires a monumental feat of engineering. Much of this relies on interferometer arrays, specifically facilities like LMA, the Atacama Large Millimeter Array down in Chile.
Okay.
We are talking about 66 massive radio antennas working together in perfect synchrony in one of the highest, driest deserts on Earth.
Wait, why the desert? Is that just to avoid rain clouds blocking the view?
It's to avoid water vapor entirely. The signals these telescopes are trying to catch from these distant galaxies are incredibly faint radio and submillimeter waves. And water vapor in Earth's atmosphere actually absorbs those specific frequencies. If you build a telescope at sea level, the atmosphere is essentially opaque. It's literally like trying to see the stars through a thick fog.
Oh, wow.
Yeah, so up in the Atacama, the air is so thin and dry that the universe just opens up to us.
Okay, so we have this massive array of synchronized dishes staring into deep space. They gather this enormous data set of 100,000 clouds. How does looking at that sheer volume of traffic fundamentally change our understanding of how gas behaves?
It provides absolute mathematical clarity. Having that volume of data allows researchers to perform rigorous statistical filtering.
Filtering out the noise, essentially.
Exactly. They can capture the effects of large-scale galactic dynamics and definitively separate the personality of an individual galaxy from the fundamental physics that govern the entire universe.
Wait, the personality of a galaxy. Break that down for me. What actually makes up a cosmic personality?
It is all the macro-level traits, like its total stellar mass, or its morphological shape. Does that have tightly wound spiral arms, or is it more of a loose, fluffy spiral? Is it an elliptical galaxy?
Okay, I see.
How fast does it rotate? What is the gravitational shear force in its disk? Those are the quirks. Those are the roundabouts and the four-way stops from your traffic analogy.
Right.
But beneath all of that macro-level personality, there are baseline immutable rules governing how a cloud of hydrogen gas behaves when it reaches a certain temperature and density.
So you just need a big enough sample size to see them.
Yes. By studying 100,000 examples across 66 drastically different environments, those local quirks just average out mathematically. The universal laws simply rise to the surface.
So we finally get to see the actual bedrock rules of star formation, completely stripped of all the local drama of whatever galaxy they happen to be living in.
Exactly. We enter a regime where definitive global patterns become visible. We are no longer just guessing if something is a Milky Way phenomenon. We can say with statistical certainty, this is how the universe builds stars, regardless of the zip code.
That sheer ambition required to catalog 100,000 individual star factories is staggering. But now that we have established this God's eye view, this massive panoramic understanding of the scale, I kind of want to pivot and do the exact opposite. Yeah, let's zoom all the way in. Let's pick just one of these 100,000 factories, strip away the surrounding galaxy entirely, and just look inside. What is actually happening in the dark?
Well, to understand the interior, we first have to look at the raw material. Giant molecular clouds, the primary sites of star formation. They are composed overwhelmingly of molecular hydrogen.
Okay.
And ironically, despite being the most abundant molecule in these massive structures, it is famously difficult to detect directly.
Let me stop you right there, because that sounds completely counterintuitive.
It does, doesn't it?
Yeah. If these clouds contain hundreds of thousands of times the mass of our sun, and they are almost entirely made of hydrogen, shouldn't the hydrogen be glaringly obvious to our telescopes?
You would certainly think so. But the universe rarely makes things that easy. Molecular hydrogen, especially deep inside these dense clouds, is incredibly cold.
How cold are we talking?
We are talking maybe 10 to 20 degrees above absolute zero.
Wow.
And because it is so profoundly cold, it exists in its lowest possible energy state. It simply doesn't have the thermal energy required to emit the kind of bright radiation, the specific wavelengths of light that our telescopes can easily pick up.
So it's just sitting there in the dark.
Exactly. It dominates the mass of the interstellar medium, but it hides perfectly.
Wait, but if the hydrogen is invisible because it's too cold to glow, how did LMA and these other arrays map 100,000 of them? I mean, you can't photograph an invisible cloud.
Right, so you don't look for the hydrogen, you look for a chemical stowaway. Astronomers use what are called tracer molecules.
Tracer molecules, okay.
Mixed in with all that freezing hydrogen are trace amounts of other molecules, most notably carbon monoxide.
Carbon monoxide, like the exact same stuff that comes out of a car exhaust.
The very same. Now, carbon monoxide is slightly asymmetric, which means even at those incredibly freezing temperatures, when it collides with a hydrogen molecule, it gets a tiny bit of rotational energy.
Oh, interesting.
And when it spins down from that energized state, it emits a very specific faint photon at a wavelength of about 2.6 millimeters.
Which is a radio wave.
Yes, a radio wave that passes right through the thick dust of the galaxy and flies straight into the dishes of ALMA.
Wow.
So we aren't actually seeing the massive ocean of hydrogen at all. We are seeing the glowing foam of carbon monoxide riding on top of it, and we use that to trace the outline and density of the invisible cloud beneath.
That is brilliant. It's like tracking an invisible man in the snow by just looking for his footprints.
That's a great way to put it.
Okay, so we have these massive, freezing, invisible clouds of gas traced by carbon monoxide floating out there. But what actually makes a cloud a star factory? Is it just a matter of accumulating enough mass in one spot?
Mass is definitely a factor, but the absolute defining feature of a giant molecular cloud is its thermodynamic state. It is a constant battle of physical forces.
Thermodynamics. So the relationship between heat, pressure, and gravity. Let's dig into that battle.
Sure. In any body of gas, the internal temperature creates thermal pressure. The gas atoms are vibrating and bouncing off each other, which creates an outward pushing force.
Like heating up a balloon, right? The air inside expands and pushes outward against the rubber.
Exactly. And gravity, conversely, is the inward pulling force. The collective mass of all that gas is constantly trying to pull every single molecule toward the center of the cloud.
So it's an outward push from thermal energy and an inward crush from gravity. A cosmic tug of war.
And the defining thermodynamic state of these molecular clouds is that they exist at temperatures so incredibly low, those 10 degrees above absolute zero. We mentioned that the thermal pressure is incredibly weak.
The outward push just isn't strong enough.
Right. It is feeble. It simply cannot prevent gravity from dominating the tug of war. The cloud is considered gravitationally bound. Gravity continuously pulls the gas inward, allowing tiny density fluctuation to grow, to clump together into cores, and eventually collapse entirely to ignite nuclear fusion and form stars.
Okay, so if I'm visualizing this based purely on what you just said, I'm picturing a giant, perfectly spherical, silent ball of freezing gas.
Right.
And because gravity is a smooth, continuous force, I'm imagining this sphere very slowly, very smoothly shrinking inward. Just a quiet, inevitable, highly organized collapse right toward the center.
And that perfectly encapsulates the classic intuitive model that dominated early astronomical thinking. It sounds completely logical if you only consider basic thermodynamics and gravity.
But I'm guessing it's wrong.
It is entirely wrong. The data reveals a critical plot twist. That smooth, quiet description fails completely.
Wrong how? Where does the smooth collapse model actually fail?
It fails because molecular clouds are not quiet, slowly shrinking spheres. They are wildly chaotic, highly fractured, incredibly violent systems. They are dominated by intense turbulence.
Turbulence.
Yes. We are talking about supersonic motions continuously ripping through the gas, constantly shattering and reshaping its internal density.
Wait, supersonic motions? Inside a gas cloud in the vacuum of space? I think of turbulence as a bumpy airplane ride. How on earth do you get supersonic winds in space?
Well, it isn't turbulence like wind flowing over an airplane wing. This is astrophysical turbulence, often magnetohydrodynamic in nature, meaning it involves incredibly complex interactions with magnetic fields.
Okay, that sounds intense.
It is. But practically speaking, imagine currents of gas flowing faster than the speed of sound for that specific medium. Because these flows are supersonic, they don't just gently push past each other.
What happens when they hit?
When they collide, they create massive shock waves that ripple through the entire structure of the cloud.
That completely shatters the picture of a peaceful stellar nursery. I mean, we usually think of gravity as this elegant, inevitable pulling force, like water circling smoothly down a drain.
Right, the smooth drain analogy.
But if you have supersonic shock waves constantly ripping through the collapsing gas, trying to form a star isn't like water circling down a drain at all. It's like trying to build a delicate house of cards while standing inside an active wind tunnel.
Building a house of cards in a wind tunnel is a fantastic visual. It captures the sheer frustration of the gravitational collapse perfectly. And this internal turbulence plays a highly complex dual role in the whole process of star formation.
A dual role. I'm really struggling to see how a wind tunnel does anything other than instantly knock the cards down. How does a supersonic shockwave actually help?
Well, on the macro level, you're absolutely right. Turbulence inhibits star formation. The supersonic shock waves hit large pockets of gas and disperse them, blowing them apart and keeping the clouds supported against overall global collapse. It acts as a massive disruptor. If the turbulence wasn't there, the entire cloud would just free fall into itself almost immediately.
So it acts as a structural support by constantly stirring the pot, basically. What is the flip side then?
The flip side happens on the micro scale. When these supersonic shock waves crash into each other head-on, they don't just scatter gas, they compress it.
Oh.
Yeah. Where the invisible winds collide, they slam gas together with immense kinetic force, creating highly localized, ultra-dense pockets.
I see.
And in those specific compressed pockets, the density spikes so high that the local gravitational pull suddenly becomes completely overwhelming. In that tiny pocket, gravity finally wins the war against the turbulence, and a star is born.
That is wild. So the turbulence is simultaneously ripping the larger nursery apart to stop the whole thing from collapsing, but the shock waves are also slamming material together hard enough to act as the spark plugs that ignite individual stars. It's both the primary destroyer and the essential creator.
It is a constant raging war between gravity trying to pull things together and supersonic turbulence trying to rip things apart while simultaneously compressing the very conditions for gravity to succeed locally. This highly specific interplay dictates the actual rate of star formation we observe across the universe.
So these clouds are literal war zones. And because they're being subjected to this intense internal violence, it stands to reason that they wouldn't be particularly stable over long periods.
Definitely not.
Which brings us to the lifespan of these structures. Humanity has a heavy bias toward thinking of everything in astronomy as being impossibly ancient and eternal. But this data set proves that giant molecular clouds are surprisingly transient, don't they?
They are incredibly fleeting. When you measure their life cycles from the initial moment the atomic gas cools and assembles into a molecular cloud to the moment the cloud is completely dispersed and destroyed, they typically only exist for tens of millions of years.
Tens of millions of years, which to our human brains sounds like an unfathomable eternity. But we really have to put that into the proper galactic context to see how fast it actually is.
Exactly. Consider the galaxy they live in. A typical spiral galaxy like our Milky Way takes roughly 200 to 250 million years just to complete one single rotation.
So if we look at a galaxy as a giant cosmic clock face, the galaxy itself takes 250 million years for the minute hand to sweep all the way around once.
Right.
But these massive star factories, these molecular clouds, they assemble, fight their internal wars, give birth to stars, and are completely obliterated before the galaxy has even spun a quarter of the way around.
They are the cosmic equivalent of mayflies. They blink into existence and vanish almost instantly on a galactic timescale. And this realization completely overhauls how we view the space between the stars. It forces us to adopt the framework of a highly dynamic interstellar medium.
Now, we've known about the interstellar medium forever, but it's historically been treated as a passive backdrop, right? Just a vast, empty bucket of loose gas sitting between the stars, waiting around to be used. You're saying this data shows it's actually an active, churning phase change engine.
Precisely. It is not a static reservoir at all. It is a violently evolving system where gas constantly cycles through very distinct thermodynamic phases.
Walk me through those phases.
It starts as diffuse atomic gas, mostly warm, loose, unorganized hydrogen atoms drifting in space. Over millions of years, large-scale galactic gravity and cooling processes gather this diffuse gas. As it cools, it clumps together, transitioning into the dense molecular phase. It becomes the giant molecular clouds we've been discussing.
The turbulent wind tunnels.
Right. Then, inside those cold, dense clouds, the shock waves compress the gas, and a few stars are born. But the violent birth of those stars, which we will dig into shortly, eventually blows the entire surrounding cloud apart.
So the cloud gets shredded.
The dense molecular gas is violently shredded, heated up, and thrown back out into the void, where it reverts into warm, diffuse atomic gas all over again. The cycle repeats continuously.
That completely shatters a major misconception for me. When you look at those gorgeous, high-resolution images from the James Webb Telescope, like the pillars of creation, you see these stunning, towering, dark patches of dust and gas silhouetted against a glowing background.
They are beautiful.
They look incredibly solid. They look like permanent monuments carved out of cosmic stone.
They really do. The visual intuition screams that they are permanent fixtures of the galaxy.
But based on what you were saying, they aren't mountains at all. They are literally much more like the ephemeral weather clouds in our own earthly sky. They are constantly gathering from an invisible vapor, raining out a small handful of stars, and then completely evaporating back into the atmospheric background.
That is the exact conceptual leap you need to make. They are weather systems on a scale of hundreds of light years. And this dynamic cycling behavior has profound implications for how we understand the survival of entire galaxies.
If the clouds are just temporary weather, how does that change the way we look at a galaxy's overall health?
It means that simply measuring how much total gas a galaxy has in its reservoir doesn't actually tell you much about its ability to form stars. Star formation is fundamentally a question of metabolism.
Metabolism, like digestion. Walk me through that.
Think of the warm, diffuse gas as raw nutrients. Having a lot of nutrients doesn't matter if your body can't process them. A galaxy must continuously assemble that diffuse gas into dense molecular clouds, run the factory briefly, and then recycle the debris.
Okay, I follow.
It's an ongoing, real-time metabolic process of assembly and destruction. The rate at which a galaxy can successfully execute that cycle determines its actual star formation rate.
So the lifeblood of a galaxy isn't just its mass, it's how efficiently it can build the factories before the materials disperse. And what the data shows is that the speed of this assembly line, how fast a galaxy can churn out these clouds, depends drastically on where you live in the galactic neighborhood. If we look at a galaxy as a sprawling city, the real estate market changes wildly depending on your zip code.
The study revealed a very distinct radial gradient across the galaxies observed. There was dramatic mathematical difference between the dense, downtown metropolitan center of a galaxy and the quiet, rural outskirts. The physical properties and lifespans of molecular clouds vary intensely depending on their local environment.
Let's start right in the downtown core, the inner regions of a galaxy. What is the cosmic real estate like there?
The inner galaxy is an extreme high-stress environment. The gravitational potentials near the galactic core are incredibly deep, meaning the overall pull from the immense density of older stars, black holes, and dark matter is completely overwhelming.
Right, there's a lot of mass concentrated there.
Because of this sheer gravitational crush, the gas densities are extremely high. Everything is packed tightly together.
Like a crowded subway car of gas. So does the assembly of clouds happen faster there?
Much faster. Because the gas is already so dense and the gravitational pull is so strong, the diffuse gas is forced together rapidly. Molecular clouds assemble almost aggressively. But the trade-off is that they also evolve and die on heavily compressed timescales.
Fast life, brutal death. If they form so easily, why do they die so quickly in the inner galaxy?
Because the surrounding environment is hostile. It's a high-pressure zone. You have intense external pressure from the ambient medium. Furthermore, because everything is rotating rapidly in a confined space, you have frequent cloud collisions.
They literally crash into each other.
Massive molecular clouds literally slam into each other like cosmic traffic accidents, which accelerates internal collapse and triggers bursts of star formation.
And if you have rapid star formation, you have rapid consequences.
Exactly. The sheer volume of newly born stars creates incredibly intense radiation fields. The internal destruction mechanisms, which we will definitely touch on, are amplified. The environment simply tears the clouds apart almost as soon as they manage to form.
So the downtown core is this high-stress, high-yield environment. Clouds are forced into existence quickly, smash together, spit out a ton of stars, and get blasted apart. Let's travel out to the suburbs then, the outer edges of the galactic disk. How does the metabolism change out there?
The outer galaxy operates in a completely different physical regime. Out there, the interstellar medium is much more diffuse. The gas is spread incredibly thin, and the overall gravitational pull from the galaxy is significantly weaker.
So the assembly line slows down to a crawl.
Exactly. Gathering enough of that diffuse, thinly spread gas to actually overcome thermal pressure and form a dense molecular cloud is a painstakingly slow process. The gravitational triggers are just weak.
For once it forms.
Once a cloud finally does manage to assemble, its internal evolution proceeds sluggishly. Without the intense external pressure and the frequent violent collisions of the inner galaxy, the cloud just kind of slowly churns along in isolation.
So you get a sluggish evolution and consequently a much lower star formation rate in the outskirts.
Which perfectly explains the radial gradient observed in the dataset. The downtown core is bright and active, the suburbs are dim and quiet.
That makes perfect sense.
But the data also highlights that this gradient isn't just a simple one-to-one reflection of how much gas is present. It's governed by a complex interplay of orbital dynamics, the physical shear forces of the spinning galaxy pulling the clouds apart, and that delicate balance between gravitational collapse and thermal pressure.
You mentioned orbital dynamics and shear forces. That brings up a fascinating point about the physical structure of these galaxies. When I picture a classic photogenic galaxy, I think of a grand design spiral.
Right, the classic whirlpool image.
Exactly, a giant whirlpool with those sweeping, beautiful, luminous arms. If a galaxy is a spinning whirlpool, how do those spiral arms actually interact with these clouds? Are the arms just made of clouds?
This is a crucial distinction. Spiral arms are not physical objects in the way a spoke on a bicycle wheel is an object. They are density waves.
Density waves, like a sound wave moving through air.
Very similar conceptually. The best way to visualize how a spiral arm affects the gas is to think of a massive moving traffic jam on a circular highway.
Okay, I'm on the highway. Walk me through the physics of the traffic jam.
Imagine you are driving on a multi-lane highway, and up ahead there is a slow-moving convoy of heavy trucks. As you and all the cars around you approach this slow-moving zone, you all have to hit the brakes.
Right.
The cars bunch up tightly behind the trucks. For a brief moment, the physical density of cars in that specific patch of highway skyrockets.
Right, you're bumper to bumper. It's miserable.
But eventually, you slowly navigate past the trucks. Once you clear them, you hit the gas, speed up, and the distance between the cars spreads out again. The traffic jam itself is a region of high density that slowly moves down the highway, even though individual cars continuously flow into it, slow down, and then flow right out of it.
Oh, wow. So the spiral arm isn't a fixed structure of specific stars. It is the traffic jam itself.
Exactly. The spiral arm is a propagating region of enhanced gravitational compression that rotates through the galaxy at a different speed than the gas itself. As the diffuse, loose gas orbits around the galactic center, it inevitably rear-ends this slower-moving density wave. It hits the spiral arm.
And that is the compression zone.
Right. The gas slams into the traffic jam. It is funneled, squeezed, and severely compressed by the enhanced gravity of the wave.
And because it's being squeezed so violently, that is the exact mechanism that forces the warm, diffuse gas to suddenly condense into cold, dense molecular clouds.
The spiral arm literally acts as a giant cosmic snowplow, forcing the gas to fragment into molecular clouds. The sudden high density triggers a burst of star formation, which is exactly why spiral arms glow so brightly with young, hot blue stars.
Because that's where all the action is being forced to happen.
Right. But remember, the galaxy keeps spinning. The gas doesn't stay in the arm forever. Eventually, that newly formed cloud rotates out of the front of the spiral arm.
It clears the convoy of trucks. It hits the open highway.
It leaves the compression zone. The external gravitational pressure plummets, the physical conditions change, and without that squeezing force, the cloud begins to naturally expand and disperse, aided by the stars it just created.
That is absolutely mesmerizing. A molecular cloud's entire life cycle is intimately physically tied to its physical commute through the galaxy. It coasts as a loose fog, rear-ends the traffic jam, gets squished into a dense cloud, frantically builds a few stars, and then evaporates the moment the traffic clears.
And by capturing this dynamic across 100,000 clouds, the researchers were able to statistically isolate these effects and mathematically prove that this density wave mechanism is a universal law of spiral galaxies, not just a quirk of the Milky Way.
But here's the thing that completely breaks my brain. We are talking about these massive, sprawling clouds. They contain hundreds of thousands, sometimes millions of times the mass of our sun in raw hydrogen.
Huge amounts of mass.
Right. And we just established that they're being subjected to this immense gravitational pressure in these spiral arm traffic jams. You would logically think, with all that raw material and all that violent squeezing, they would be incredibly productive star factories.
You think so?
But this immense data set confirms a shocking secret about their actual productivity, doesn't it?
It confirms what is arguably the most striking, counterintuitive physical law in modern astrophysics. Despite all that mass, despite all the relentless crushing force of gravity, giant molecular clouds are unbelievably, almost comically, inefficient at doing the one thing they are known for.
Let's put a hard number on it. How inefficient are we actually talking?
We are talking about a universal 1% success rate. On average, over its entire lifespan, a giant molecular cloud will only convert about 1% of its total available gas mass into actual stars before the entire cloud is destroyed.
Let me repeat that just to make sure I am grasping the scale of the failure.
Yeah.
1%.
Roughly 1%. The remaining 99% of the carefully assembled hydrogen is simply blasted back out into the interstellar medium, completely unused.
I really need to push back on this because it offends my sense of basic logic.
I don't blame you.
Gravity is arguably the most relentless, inevitable force in the universe. If you have 1,000,000 times the mass of the sun pulling inward, creating an inescapable gravity well, how can the factory possibly shut down at 1%?
And it's hard to wrap your head around.
Let me give you a terrestrial analogy. If I own an industrial bakery, I purchase 1,000,000 pounds of flour. I build the building, I hire the staff, I preheat the massive ovens.
Okay, you're invested.
Heavily invested. And after all that incredible logistical effort, I managed to bake exactly 10 loaves of bread before my entire bakery spontaneously explodes and scatters 990,000 pounds of flour across the city.
That would be a terrible business model.
I wouldn't just be a bad baker, I would be in absolute defiance of physics. How is nature so remarkably terrible at making stars?
The exploding bakery is actually a terrifyingly accurate analogy for what is physically happening. And it's important to note that for decades, astronomers suspected this. They observed individual star-forming regions in the Milky Way, like the Orion Nebula, and noticed that there was far more gas present than newly formed stars.
But they weren't sure.
There was always a lingering, nagging doubt. Was Orion just a weird local condition? Did our local bakery just have a bad day?
Right, a small sample limitation. We talked about that.
Exactly. But analyzing 100,000 clouds across 66 galaxies entirely removes that doubt. It definitively proves that this extreme 1% inefficiency is a universal physical law. Whether you are in the chaotic, dense inner core of a massive spiral or the quiet, diffuse outskirts of a dwarf galaxy, the 1% rule holds true. It is a fundamental property of how baryonic matter behaves in the universe.
Okay, so the universe is universally a terrible baker. But there has to be a physical mechanism. It can't just be cosmic bad luck. If gravity is constantly pulling all this mass together, what force is strong enough to overpower 1,000,000 solar masses of gravity and force the factory to shut down so early? What is the detonator inside the bakery?
Well, to find the detonator, you have to look at the product itself, because the inefficiency isn't a failure of gravity. It is an active, violent sabotage by the very things the cloud is trying to create.
Wait, really?
Yes. This brings us to the core concept of galactic self-regulation, driven by a phenomenon known as stellar feedback.
Stellar feedback. So the newly born stars are actively sabotaging their own nursery.
Intentionally and viciously. As soon as a molecular cloud successfully forms a cluster of stars, particularly massive, hot O and B class stars, the clock starts ticking. These newly formed stars immediately begin injecting absolutely immense amounts of kinetic and radiative energy directly back into the surrounding gas that birthed them.
They fight back against the gravity of the cloud. How? What are their weapons?
They possess a terrifying arsenal of astrophysical weapons. First, you have extreme ultraviolet radiation.
Like sunburn, but scaled up.
Scaled up to the point of breaking physics. These massive newborn stars burn incredibly hot. They emit UV photons with so much energy that when they strike the surrounding cold molecular hydrogen, they literally rip the electrons away from the atomic nuclei. This process is called ionization.
So it's shredding the molecules apart.
And heating them violently.
Yeah.
The gas goes from 10 degrees above absolute zero to 10,000 degrees almost instantly.
Oh, wow.
Yeah. This creates an expanding bubble of superheated plasma. Because the plasma is so hot, the thermal pressure we talked about earlier skyrockets.
Oh.
It pushes outward with immense force, literally cooking and carving the cold cloud from the inside out.
So the first weapon is a giant, expanding cosmic blowtorch. What's next?
The second weapon is the stellar wind. Much like our own sun, constantly emits a stream of charged particles. The solar wind, these massive newborn stars, drive incredibly powerful supersonic outflows of material. These winds carry huge amounts of momentum. When they slam into the surrounding cold gas, they act like a continuous hurricane-force battering ram, physically eroding the dense clumps and pushing the gas out of the gravitational well.
The blowtorch and the battering ram, and I assume there is a grand finale.
The grand finale is catastrophic. The most massive of these stars, the ones generating the most UV light and the strongest winds, are evolutionary speedrunners. They burn through their internal nuclear fuel incredibly quickly.
How quickly?
In just a few million years, which is nothing on a cosmic scale, they reach the end of their lives, collapse, and detonate as supernovae.
The ultimate explosive detonator.
A single supernova releases an incomprehensible amount of energy.
Ugh.
The shockwave from a supernova is more than enough to completely shatter and disperse whatever cold gas managed to survive the UV radiation and the winds. Between the blowtorch, the battering ram, and the final bombs, the collective stellar feedback entirely halts further star formation. The stars effectively destroy the factory, limiting themselves to that 1% efficiency.
Okay, so the sequence is: gravity pulls the gas together, turbulence sparks a few massive stars, and the immediate violent reaction of those stars being born is what blows away the remaining 99% of the gas, stopping gravity in its tracks.
That's the sequence.
It's a localized self-destruct sequence, but it feels so wildly wasteful. Why would the mechanics of the universe evolve to operate this way?
Because if it didn't operate this way, the universe as we know it would be dead. Let's run a thought experiment. Imagine the alternative. What if giant molecular clouds were 100% efficient? What if there was no stellar feedback, no UV blowtorches, no supernovae? Gravity just happily pulls all 1 million solar masses of gas together into a massive cluster of stars without any resistance.
I assume you'd just get a spectacular, blindingly bright galaxy very quickly.
You would. In fact, if clouds were 100% efficient, they would convert all their available gas into stars in a single free-fall time, basically instantaneously in cosmic terms. The star formation rate of the galaxy would skyrocket by a factor of 100, and the consequence of that would be unequivocally catastrophic.
Catastrophic how? What's wrong with a lot of stars?
Yeah, well, a galaxy is a closed ecosystem. It only has a finite set amount of gas to work with. If it converted all of its gas into stars at 100% efficiency, it would rapidly exhaust its entire fuel supply in a cosmic blink of an eye. There would be an initial blindingly bright flash of starburst activity and then nothing. The raw material would be entirely gone. The galaxy would go permanently dark and dead, populated only by aging, cooling stars, unable to ever form a new star again.
I see. It's like building a bonfire in the woods.
Walk me through the bonfire.
Well, if you have a massive pile of dry winter wood and you just dump all of it onto the fire at the very beginning, you get this massive, towering, roaring flame. It's incredibly bright.
But very brief.
Exactly. It burns through all the fuel in an hour. You're left with nothing but cold ashes for the rest of the long, freezing night.
It's an excellent analogy, but we need to add the stellar feedback element to it. It's a bonfire where the wood is packed with dynamite.
It's dynamite.
Yes. Imagine every time the fire gets a little bit too hot, a small stick of dynamite explodes in the center. The explosion doesn't put the fire out entirely, but it violently kicks the unburnt logs away from the center, scattering them across the clearing.
It blows the fuel away from the heat source. It prevents the fire from consuming everything at once.
Exactly. The logs are scattered, they cool down. Eventually, somebody rolls them back together in a different part of the clearing, and a new small fire starts. Then another explosion scatters them again. This violent, constant disruption forces the fire to burn low and slow. It ensures you have enough wood to keep a small fire going, not just for an hour, but for billions of years.
So the staggering inefficiency isn't a failure of nature. It's a built-in safety valve.
It is a fundamental, absolutely necessary condition for the long-term survival of a galaxy. This feedback-driven disruption is not a secondary, accidental effect. It is the core regulatory component of the star formation process.
It's what keeps the whole thing running.
It ensures that the galactic gas reservoir is not rapidly exhausted. It allows galaxies to sustain a steady, slow trickle of star formation over the entire 13.8 billion-year history of the universe. It is the ultimate form of self-regulation.
That completely flips my entire understanding of destruction in the cosmos. I mean, we are always taught to view a supernova as a tragic ending, the death throes of a massive star. But mathematically, that explosion is a protective measure. It's intentionally shattering the nursery to save the remaining 99% of the fuel for future generations of stars.
That is the exact paradigm shifts this data forces upon us. And this delicate, violent balance of creation and destruction doesn't just keep the galaxy glowing with starlight over billions of years. It actually drives the fundamental chemical evolution that allows for the creation of everything we care about, including ourselves. Which brings us to the massive, universe-spanning ripple effects of this 1% rule.
Let's talk about those ripple effects, because this continuous billion-year cycle, a cloud forming, making a few stars, and then being violently destroyed, has massive implications for what a galaxy is actually made of.
It does. And to understand the magnitude of those implications, we have to remember what stars actually do on a chemical level. Stars are not just light bulbs. They are the sole manufacturing plants for heavy elements in the universe.
Right, because if we rewind the clock to right after the Big Bang, the universe was incredibly chemically boring. It was essentially just a vast ocean of hydrogen and helium.
Exactly. Just the absolute lightest, simplest gases. There was no carbon, no oxygen, no silicon, no iron.
None of it.
Every single heavy element in the universe is forged inside the crushing heat and pressure of a star's core through nuclear fusion. And when those massive stars detonate as supernovae, they don't just destroy their parent molecular cloud, they obliterate themselves. And in doing so, they blast all those newly forged heavy elements out into the interstellar medium.
They are continuously enriching the soil of the galaxy.
Precisely. Now connect that to the 1% rule we just discussed. Because the universe strictly and violently regulates star formation to that 1% efficiency, the rate at which new stars form, and consequently, the rate at which massive stars explode, is very tightly controlled.
So it's not all happening at once.
Therefore, the rate at which a galaxy becomes enriched with these heavy elements is a slow, steady, gradual process that takes billions of years.
But why is the speed of that chemical enrichment so critical? Why wouldn't we want the galaxy to forge all its heavy elements instantly?
Because the speed dictates what kind of planetary systems can successfully form. If a galaxy lacked feedback and burned through all its gas instantly, it would produce a massive, immediate burst of heavy elements, but all the hydrogen gas would be gone. There would be no raw material left to actually form new, stable solar systems that incorporate those heavy elements.
It would be a galaxy full of metal dust, but no gas to bind it together into new stars.
Right. But because of this slow, highly regulated, inefficient release, the overall metallicity, the amount of heavy elements in the galaxy's gas, gradually increases over billions of years, while leaving plenty of hydrogen untouched.
And as the interstellar medium gets richer and richer in these elements,
the subsequent generations of molecular clouds that form out of that enriched gas have a completely different chemical makeup. They now contain the raw building materials, the carbon, the oxygen, the silicon, the iron necessary to eventually condense into protoplanetary disks, and ultimately complex rocky planets around their new stars.
And on those stable, rocky planets, bathed in the steady light of a long-lasting star, you have the necessary conditions for complex chemistry and eventually biology.
Exactly.
I want to take a second and direct this specifically to you, the listener, because the chain of causality here is incredibly profound. Think about the physical reality of your own body right now. The iron flowing in the hemoglobin of your blood, the calcium that forms the structural matrix of your bones, the carbon in your DNA, all of it, every single heavy atom, exists in the exact quantities it does on this specific planet solely because giant turbulent gas clouds in deep space are terribly, violently inefficient at their jobs.
It is a staggering philosophical connection to make, but it's 100% mathematically and scientifically accurate. The slow, gradual formation of a stable solar system like ours, one capable of supporting an intricate biological biosphere, depends entirely on the fact that molecular clouds constantly blow themselves apart. We literally owe our existence to the universe's exploding bakery.
That is just awe-inspiring.
Yeah.
But this universal law of inefficiency doesn't just explain our own local history in the Milky Way, does it? It also gives astrophysicists a sort of Rosetta Stone for looking backward in time.
It does. It provides a critical framework for interpreting observations of the deep universe. When astronomers use telescopes to observe high redshift galaxies that are incredibly far away, they are effectively looking back in time. They are observing the universe as it existed billions of years ago, during epochs like cosmic noon when star formation was at its peak.
Because the light took billions of years to travel across the void to reach our telescope mirrors.
Correct. Now, because of the extreme distances, we simply cannot resolve individual molecular clouds in a galaxy that is 10 billion light years away. The optical resolution limit of our telescopes just isn't there yet. We can only see the overall glow of the galaxy.
Right.
But because this massive new data set has proven that the 1% efficiency rule and the turbulence gravity war are universal laws of physics across 66 diverse local galaxies,
We can confidently apply those laws backward because the fundamental physics of hydrogen gas, gravity, and thermodynamics don't magically change just because you go back in time.
Exactly. If the same basic physical principles apply, then we know that the inefficiency, the supersonic turbulence, and the transient self-destructing nature of molecular clouds were the exact key factors shaping the evolution of galaxies during the very dawn of the universe. We can use our detailed, high-resolution understanding of local star factories to accurately model how the earliest galaxies laid the initial, chaotic groundwork for chemical enrichment.
It bridges this incredible gap between the microscopic scale of a single newly born star blowing a bubble in its nursery and the macroscopic scale of the entire 13.8 billion-year history of the universe.
And that realization represents the major conceptual shift occurring in modern astrophysics right now. We are definitively moving away from viewing galaxies as just a random assortment of stuff, gas and stars just floating near each other, driven by one or two dominant forces. We're moving toward viewing galaxies as highly complex, deeply interconnected, nonlinear, self-regulating systems.
It sounds exactly like studying a biological ecosystem on Earth.
It is practically identical to an ecosystem. It is a system where the overall evolution of the galaxy emerges naturally from the chaotic interaction of multiple mechanisms operating across wildly different scales.
Everything is connected.
The large-scale galactic dynamics, the rotation, and the spiral density waves dictate the macro conditions under which the clouds form. Inside the clouds, the microscopic interplay of thermodynamics and supersonic turbulence dictates where the stars ignite. Those stars then unleash radiation and supernovae, feeding immense thermal energy back into the macro system, completely altering the structural conditions for any future cloud formation.
It is an endless, continuous feedback loop where absolutely no single component can be isolated or understood on its own. The entire galaxy acts as the anvil that shapes the cloud acts as the turbulent forge that births the star, and the star acts as the hammer that shatters the cloud, which ultimately alters the shape of the galaxy.
Ultimately, it underscores the profound importance of scale and interconnectedness. Microscopic physical processes, like the ionization of a hydrogen atom by a single UV photon, scale up to influence the survival of entire galaxies over billions of years. By bridging these enormous gaps in scale, from the atomic to the galactic, we get a much more integrated, holistic view of how the universe actually operates.
It's all one big picture.
To understand something as seemingly straightforward as the birth of a single star, you have to concurrently understand the localized turbulence within a cold cloud, the broader gravitational environment of a spinning galaxy, and the violent feedback mechanisms that tie them all together.
It really is a beautiful, terrifying, perfect loop. And it is wild to take a step back and think about how much ground we've covered in this conversation. We started by zooming way, way out, looking at this monumental data set of 100,000 clouds across 66 different galaxies. We saw how this massive scale finally allowed us to strip away the local quirks of individual galaxies and prove that we are looking at universal laws of physics.
We moved entirely beyond the small sample limitations of the past to see the undeniable global patterns.
Right. And from that God's eye view, we zoomed all the way down to witness the actual physical environment inside these invisible star factories. We learned that they aren't peaceful, quiet, slowly shrinking spheres of gas, but terrifying war zones. A supersonic, turbulent war between the crushing inward pull of gravity and the chaotic outward-pushing shock waves of freezing gas.
An environment where building a star is literally like trying to assemble a house of cards inside a magneto-hydrodynamic wind tunnel.
Exactly. We discovered the shockingly short lifespan of these sprawling clouds, that they are the cosmic equivalent of mayflies, living for just a brief, violent moment while the galaxy slowly turns around them. And we tracked their life cycle as they commute through the galactic traffic jams of the spiral arms, condensing out of the fog only to evaporate back into it.
It paints a picture of a dynamic, constantly cycling interstellar medium, a universe defined by constant transformation rather than static permanence.
And perhaps most mind-bending of all, We explored the incredible 1% rule, the realization that the violent, explosive destruction of these clouds by their own newborn stars isn't some tragic, wasteful failure of nature. It is a vital, intricately tuned, self-regulating safety valve. It's the dynamite in the bonfire that keeps the flames burning low and slow, ensuring that galaxies stay alive long enough to slowly forge the heavy elements required for rocky planets, complex chemistry, and ultimately for us to sit here and talk about it.
It provides a completely integrated, holistic view of a delicate balance of cosmic forces.
It really does. And it leaves me with one final thought, something I want you, the listener, to seriously mull over the next time you look up at the night sky. We have spent this entire conversation learning that galaxies are incredibly complex, highly interconnected, self-regulating systems. They actively and violently throttle their own metabolism, their rate of star formation, to ensure they survive for billions of years, rather than burning out in a single catastrophic flash. It really makes you wonder, at what point of complexity do we stop thinking of a galaxy as just a massive dead collection of rocks, dust, and freezing gas, and start thinking of it as a single macroscopic organism actively fighting to keep itself alive?
That is a profoundly challenging perspective. The strict dividing line between astrophysics and biology starts to feel very thin, almost arbitrary, when you look at massive systems that have that level of intricate self-preservation built directly into their physics.
It really does. Thank you so much for joining us on this exploration of the universe today. It has been an absolute pleasure to unpack the hidden mechanics of the cosmos with you. Tonight, if the weather cooperates and the sky is clear, I highly encourage you to step outside, look up into the dark, and try to see past the ancient illusion of peace. Look at those quiet, twinkling stars and see the incredible, violent, life-giving chaos hiding right behind them.